Hi everyone, so this is the third video in the AVL tree series, and in this video we're going to go through the basic insertion algorithm for an AVL tree. Now we're going to leave doing an example for a different video just so that the videos aren't overly long, but let's talk about how to do an insertion, okay? So the basic AVL tree insertion algorithm starts off by doing a binary search tree insertion. So the first part of the algorithm is not different than what you already know about binary search trees. You take a value, you compare it against the root node, and if it's bigger, you put it to the right, if it's smaller, you put it to the left. Then you compare against the child node, and either it goes left or right, and you kind of work your way down the tree until you find an empty subtree, and that's where you make your new node. So that's the basic binary search tree algorithm. Now, if you stop there, BST, that's the BST algorithm right there. What AVL tree does after that creating a new node part is it actually goes back up the tree and it looks at every single node that you had compared against while you were inserting. Now, because you were putting a new node in and it affects all the trees that you had compared against, those are the ones where the balances may be off. And remember that height balance, the height of the node's balance represents whether or not the entire tree is height balanced. So what we want to do is we basically want to check the balances of every node all the way back up to the root, starting with where you had done the insertion, and just sort of work your way up. When you get to the root, you're done. Okay? Now, if at any point while you are checking these balances, you reach a node where the balance is not either 0, +1, or -1, it means that the tree at that point is not it's not height balanced. That node is wrong. It's too tall on one side or the other. And so what you have to do is you have to apply a rotation to fix it. Now, there are two general types of rotations, one called a single rotation and one called a double rotation. And these will fix your trees. Which one you do depends on the way that the tree is off balance. Okay, so all of that other stuff is basically which way do we rotate, and how do we know if it's single or double? Okay, so a picture's worth 1,000 words, but that's the basic algorithm. Let's take a look and see what a rotation is, and then we'll go from there. So this is a picture of a tree rotation, okay? Oh, just realized this is not, hold on, sorry, technical issue. There we go, sorry, I just realized my thing wasn't connected. Okay, so here is a tree rotation, okay? Now, in this case, what we have is we have a tree over here that I'm representing with a bunch of circles and triangles. So the circles A and B represents two nodes. A is the node that is in this case, it will be +2. Okay, and we'll talk about why it's +2 in this case. So this is the one that is completely not correct. B is the child that is on the too tall side. And what you do with a rotation is you effectively lift one side and sort of push the other side down. So the way that you visualize this is you sort of say, okay, it starts out as this picture on the left over here. Okay, so you start here. And what we're doing is we're basically sort of spinning this thing around. So imagine that it's kind of like two weights that are sort of over a pulley, right? So if you imagine sort of like a little pulley system and you sort of have a rope and there's like two weights, you're sort of like lifting one side and the other side kind of drops down. So if you think of it like that, okay? So right now, there is too much on this side. Okay, the right hand side is too far down. So what you're going to do, what the rotation does, is it effectively shifts the nodes around so that it's more on the other side. So think of it like that. And a rotation is done by effectively doing that in terms of a binary search tree, and you end up with the picture on the right. Now you look at that and you go, okay, so that seems kind of complicated. Like, how do we even like code this thing, right? But it turns out that it's actually not all that complicated. So the good thing is that each of these triangles over here represents entire subtrees. Now, what it means is that if y over here is actually representing a tree that looks like this one, for example, we don't touch anything within that particular subtree. We leave it alone. So after we finish the rotation, anything that's inside the triangles is exactly what they were before we did the rotation. So everything inside Y stays in exactly the same configuration. Similarly, everything inside X stays exactly what it was before and after, and everything in Z is the same. So the only things we have to change is the way that these five things, A, B, X, Y, Z, are linked to each other. Okay? Now, A is a node somewhere in the tree. So is B. So what it means is that they will be pointed to by some pointer from somewhere else in the data structure. So over here, we have a pointer to A. That pointer comes from either the root underscore of your tree, or it will be the node, like the left or right pointer from some node somewhere else. Okay. But effectively, it's a node, it is a pointer to A. Okay. Now, when we finish, that same pointer must be made to point to B instead of A. So obviously, this is changed. This pointer has changed. This pointer used to point to A, now it points to B, it's changed. Now, what else has actually changed in this picture? Well, A used to point to B. So A's right pointer here, A's right, pointed to B before we did the rotation. Afterwards, A's right pointer, which is over here, it now points to Y instead. Okay, so obviously that pointer has also changed. Now, B's left pointer, which is over here, it used to point to A. When it's finished, it points to the root of Y. So obviously, that has also changed. So those three pointers are actually different. They're pointing at different things than they used to. Now, if we think about that, what hasn't changed is actually this pointer right here, as well as this pointer right here. So A's left was pointing at X beforehand, and after the rotation, it still points to X. B's right pointed to Z beforehand. B's right still points to Z afterwards. So out of the five pointers that are in this diagram, only three of them changed. So the entire rotation algorithm really comes down to changing those three pointers without actually losing any of the five components involved. So don't lose A, don't lose B, don't lose X, Y, Z, and just rearrange what those pointers point at, and you're fine. So rotations are simply pointer reassignments. That's all they are. You literally say pointer A points to this other thing instead, as opposed to being this really, like very complex algorithm. They're actually more complicated to draw than they are to code. Okay. So in total, you probably have to do a few extra pointer reassignments so you don't lose a node, but you're talking about 5 lines of code to do a rotation, and they're all assignments. Just don't lose a tree or a node while you're doing it, and that's pretty much all there is to it. So this rotation effectively pushes the nodes from the right subtree into the left subtree. That's why if you take a look, it looks like this is drawn with this right hand side being taller, and now the left hand side is taller. So that's what a rotation does. Now sometimes though, this is not the taller one. Maybe it's this side that's taller, right? So you have sort of the opposite direction rotation, which is represented by this drawing, but it's the same idea. You're still only switching 3 pointers. This one, okay, let's be consistent. This one, okay? this one, okay, and also this one. So those are the 3 pointers that actually have to change for the right rotation, but that's it. Everything else stays the same. Nothing else has changed. So left and right rotations, in the right rotation, you basically, it's too tall this side, so you switch it to the other side. So, um, and in fact, you can actually think of it as if you go from the picture on the left to the picture on the right, that's left rotate. If you go from the picture on the right to the picture on the left, then it's right rotate. That's pretty much all there is to it. It depends on like how you view this. But I find it easier actually to draw it separately. So I don't know which one you prefer, but effectively that's left and right rotate right there. Now, so this is effectively called a single rotation because you only rotate once. Now, the way that you how do you know that you're going to do a single rotation? Well, first of all, um, or how do you know which rotation, left or right? How do you know that? Let's start with that question. So if this value here is +2 in A, okay, if the balance is +2, then you're going to be doing the left rotate. Because +2 means the right-hand side is too tall, right? Like this side is too tall. So what you want to do is you want to lift this side up, like shorten it, and make the other side taller. So you do the left rotate if your right side is too tall. So if it's +2, use the first picture as the way you do your rotation. Now, if the left-hand side is too tall, then the balance here will be -2. And so you're going to do the other rotation. Okay? So +2 for the first, if it's +2, you use the first one. If it's -2, you use the second one. Left-hand side too tall, move it to the right, shift it to the right. Okay? Now those are single rotations. There is also an idea called a double rotation, and it is represented by this diagram. Now, a double rotation has to occur if the nodes are off balance on opposite sides. So what this means is that we use a double rotation if, okay, so obviously in this diagram, this one is it's taller on the right. That's why we're drawing all the things on the right. So that means that this value must be +2. And now, and down here at the B, the balance here is a -1. Okay, so this indicates that I have to use a double rotation. So at A, the right side is too tall. At B, the left side is too tall. And when that happens, we do a double rotation. Now, in the case of single rotations, you do this when A is +2 and B is too tall on the right. So Z is the one that is big. Z will be taller than Y. Okay, so Z's too tall, so we have to do a rotation. But it's +2 and +1. So it's the right side is the side that is too tall in B. Similarly, for this one, if this is -2 and B is -1, then we're going to do a single rotation. Now, what does it mean? It means that effectively what you do is you look at the sign. If the sign is the same, then you do a single rotation. Okay, so +2 +1, single rotation. -2 -1, also do a single rotation. But if the signs are different, you have to do a double rotation. And a double rotation takes you from this to this. Okay, now you look at that and you go, why is this called a double rotation? Well, it's called a double rotation because you actually did 2 single rotations at different levels. Okay, so the reason why it ends up as this is the end result. Okay, but what you are actually doing in a double rotation is you're doing 2 single rotations at different levels to different trees. So what happens first in a double rotation is you actually take this and you rotate B and C around. So right now C is this B is too tall on the left. So when you do the double rotation, you sort of rotate it around so that um, it becomes taller on the right. So the first step of a double rotation, okay, is actually this one. That's why you call it a double rotation, okay? So if you rotate here, then the result would be this, because you're just sort of shifting that part of the tree the other way. Once you have done that, you then rotate around the A. So you're going to do one more rotation, and this time at a different level, okay? So what that will do is it will make C. So what you're saying is that A is too tall on the right, and you're just simply doing a rotation now, the same single rotation. And you end up over here, okay? So if we're thinking about it in terms of the diagram, okay, the original rotation diagrams, what we did was we first applied a right rotate at level BC. So what that means is we took this one. I actually have the diagram pictures here. Okay, so this diagram, okay, so this function right, this part right here, we applied it to this tree right here. So we sort of viewed the tree as if the top part of it didn't exist. We said, okay, this thing, that is the same as this part right here. Okay, so our A is called B over here, our B is called C over here. X, Y, Z are what they are. And then, as a result of doing that rotation, what we did was we made C the root and B its right child, and so on. So we simply turned this, we basically applied this thing and got this part out of it. So after the rotation, this part is this part right here. Okay, so they're kind of linked. Okay, so you ignored the part with A and W, and you only did this. And then as a result, the subtree became this. You then do another rotation. And here, instead of viewing it like that, what you did was you said, okay, let's pretend that the tree, this is the thing that is off balance, right? So this is our A in this diagram. Our B in this diagram is actually called C, okay? And our Z, this is, oops, this whole thing here was our Z. This is our B, A is still A. This is our X, this is our Y. So if we're looking at it in terms of that, this diagram over here, that's what this is, okay? A is A, C is actually B, X is W, Y is X, and Z is the entire subtree involving B. So when we finished, okay, this is our A, this is our B, this was our X, okay? Oh, sorry. I'm sorry, that's bad. This was our B, this was our A. This is X, this is actually the Y in that diagram. This whole thing is the Z in that diagram, okay? But effectively, this is still a rotation. We're simply doing this operation here and applying it to this tree over here. That's why it's called a double rotation, because you're doing two rotations as opposed to one. Okay, so you can sort of imagine it this way. Okay, so imagine that what you did, okay, over here is you first did this and then you did that. It's kind of like a little dance. Okay, 1, 2. Okay, so you rotate once, then you rotate again, but it's at a different level. So you have to start low, then you work your way up. Okay. So over here, okay, so step one, step two, you have to do it from the bottom up. So you have to rotate the bottom bit first, then you can rotate the top bit. Okay, so this is step two. This green part is step one. But at the end of the day, this is the tree you end up with. So you don't actually have to like draw two diagrams. That's sort of silly. That's just why it's called a double rotation. I highly recommend that you simply start here, identify A, B, C, W, X, Y, Z, and then get to this point directly. It's much faster than to sort of look at it as two separate rotations. That's just two steps. Okay, so this is a double rotation. Okay, so you apply, and there are, of course, mirror images. So this is a double rotation if it's +2, -1. And there is another version of it where it is in the opposite direction. Sorry, it's over here. So I actually did diagram it out later in the notes, but it's here. Okay, so the opposite version, um, like this one goes this way, ABC, and this one goes this way. And you use this version if this is -2 and +1. Okay, so what it comes down to is simply this. Okay, and this is sort of the important takeaway from this. Which rotations do you do? So here's a mnemonic to help you remember. Same sign, single rotation. Different sign, double rotation. Okay, so that's sort of the key. Now, how do you remember it? Well, same starts with S, so does single. Different starts with D, so does double. So if the signs are the same, single rotation. If the signs are different, double rotation. Okay, SSDD, right? So they go together. Okay. So that is pretty much it for this particular video. In the next video, I'll show you how to actually use this, how to use these rotations. We'll do an example. Okay. That's it. Thanks, everyone.